Okay, welcome back after the coffee break and before the buy your own coffee break. So our next speaker will be Shubhangi, and she'll be telling us about proximity gaps for resolving.
So thanks, Ram Prasad. And again, thanks to the organizers for organizing this amazing event. It's great to be here. Thanks for inviting me. I will be talking about proximity gaps for Reed-Solomon codes. This is based on joint works with Ellie, Dan, Lior, Yuval, and Swastik. Okay, so the plan for the talk is I'll tell you what the question is about. The proximity testing question for low-degree polynomials, and I'll talk about a specific protocol for it. And the mathematically most interesting part of that is a very fundamental property that Reed-Solomon codes have. This is proximity gaps for Reed-Solomon codes. Most of the talk I'll be talking about that, and then we'll end with some open questions. Okay, so the setting is the following. So there's some underlying finite field, FQ, and there's some subset of the fields. This is, let's fix some subset of size n. And let's think of d being some parameter less than n. Think of it as 0.1 n. This is going to be the degree of the underlying Reed-Solomon code. And so you have this domain of size n. Let's imagine that there's some function written on this domain. So at every point of the domain, you have some element of FQ written. And you want to check, you have query access to F. We want to check, is F a low-degree polynomial? So how would you check it? To check if it's a low-degree polynomial, you'll have to make a lot of queries into F, to a linear number of queries to check if it's low-degree. What if you want to just check if F is close to a low-degree polynomial? How many queries do you need to make then? It's not hard to see that you still need to make a linear number of queries to even check closeness to low-degree polynomials. So without additional help, you need lots of queries. Let me just set up some notation. So I'll say RS of FQSD is the Reed-Solomon code over the field FQ. The evaluation domain is S, and we're looking at degree D polynomials. And everyone is very familiar with this code now. We can view the code words as each code word is a point in the space FQ to the n. And this is a very good error correcting code. So given the truth table of a function f, you can view f as a point in FQ to the n. And verifying if f is a closed degree polynomial is equivalent to verifying if f is close to the Reed-Solomon code. Okay, so we're looking at the question of testing proximity to the Reed-Solomon code. And like I said, without additional help, it's not hard to see that you need a linear number of queries into f to check if f is even close to a low-degree polynomial. What if you want to do this in sublinear time? There is a very natural notion of an interactive protocol between a prover and a verifier, where a prover with interaction can convince the verifier that this function is close to a Reed-Solomon code. So this is the model of IOPPs. I won't go into too much detail. I just want to somewhat informally talk about it to motivate the problem of proximity gaps for Reed-Solomon codes. So you have a prover and a verifier. The prover writes down some string. The verifier sends a query. The prover can write down another string. The verifier can ask a query. And after some interaction, the verifier agrees to accept or reject F. And this model, you can talk about the completeness. So if your function has the property, whatever the underlying property might be, and in our case, we'll be testing closeness to low-degree polynomials. If F has the property, you're hoping that the verifier you want the verifier to be convinced with probability 1. And if F does not have the property, if you're far from the property, you hope that the verifier will reject with high probability, no matter what prover is there and what the prover outputs. You want to reject with high probability. And IOPPs are a means for weak verifiers to delegate computation to powerful provers. And one popular and a practically impactful approach is to get IOPPs for general computation using IOPPs for Reed-Solomon codes. So I'll be talking about these interactive protocols for testing proximity to Reed-Solomon codes. They are a tool for getting protocols for general computation. How that happens, I will not be describing. Let's talk about these interactive protocols for testing proximity to Reed-Solomon codes. So I'll focus on a particular protocol, the Fry protocol. It's perhaps the most elegant and cleanest and easiest to describe protocol for testing proximity to Reed-Solomon codes. We know there are multiple protocols and there are improvements to Fry, but this is a very natural and clean protocol. So let's talk about this one. It has so I'll give you a protocol, I'll quickly describe it, where the prover in this protocol runs in linear time, and the verifier runs in only O of log n time, with O of log n queries, O of log n rounds, and there's nice concrete, simple protocols with concrete small numbers, and have this protocol plays an ingredient in several zero-knowledge proof systems. Okay, so we'll talk about this protocol, and then we'll see where does proximity gaps for Reed-Solomon codes, how it appears, and what is proximity gaps for Reed-Solomon codes. Yes? N is the size of the set S. Yes. Think of Q as polynomial in N right now. But it's an interesting question, what does Q have to be relative to N? We're talking about Reed-Solomon codes, so Q has to be larger than N. So you can talk about Q equal to N, Q being N square, N cube. We will talk about Q versus N when we get to more concrete parameters. But yes, thanks. N is the size of the domain S. So I'm going to tell you this protocol, or at least a high level of the protocol, but the main building block of the protocol is a 2-to-1 map. So I'm given a function f on a domain of size n, and I want to test if f is low degree. And the main building block is a scheme for reducing, checking if f is low degree on a domain of size n, to checking if another function f prime is low degree on a domain of size n over 2. So after one round of the protocol, you kind of half the domain, and then you iterate this log n times, and that's how you build the protocol. So let me describe what this 2-to-1 map is, which takes a function f on S to a function f prime on S prime. And I'll describe this map, but the nice property of this map is that each entry of f prime just depends on 2 entries of f. So there's some locality which you can in this construction, so you can check consistency that this hashing was done correctly. And if f is low degree, we'll see that f prime is low degree. If f prime is far, we'll show that, if f is far, we'll show that f prime must be far. And so once you can get such a map where with this locality property where we can reduce testing of low degree, closeness to low degreeness of f to testing of low degreeness of f prime, one can iterate this to get a protocol for checking for efficiently checking low degreeness of f. So let me describe what this very quickly. Let me describe what this 2-to-1 map is. So if f was a degree d polynomial, then just like you do in FFT computations, you can break f into its odd and even parts and write f as g of t square plus t times h of t square. You can find 2 polynomials, g and h. So if f is degree d, you can find g and h of degree d over 2. And you can write f as a polynomial, as some polynomial combination of g and h. So, and then notice that there's some locality in this, in the definition of, so the evaluation of g at any point depends on the values of f at 2 points. And the value of h at any point depends on the value of f at just 2 points. So if f is an arbitrary function also, I can still define these new functions g and h, where entry by entry g and h just depend on 2 queries into f. Good. So given f, given a function f, I can define these 2 functions g and h. And if f is degree d, g and h are both degree d over 2. Okay, so from one polynomial of degree d, I got 2 polynomials of degree d over 2. Now let me define f prime as a random linear combination of g and h. So G and H were both degree d over 2, F prime will also be degree d over 2. So in this manner, I got from one function of degree d to a single function of degree d over 2. Let's take this offline and let me think about it. Yeah. Yes. Good. So good. You can check consistency. So each entry of F depends. So even if you have F, you can define F prime, and each entry of F prime depends on two entries of F. So there's some locality. It's easy to see that if F is low degree, then F prime is low degree. And what we will show, which is not immediate, is that if F is far from low degree, then F prime with high probability is far from low degree. Okay, but this third property is non-trivial and will be the focus of the talk. Think of Z as a random, not as formal variable, but a random field constant. So this is a random map from F to F prime. So think of Z as the seed. So Z is a random seed, and given F, this is a random map from F to F prime. In fact, in the protocol, Z will be something that the verifier will provide. So there's F, which is written initially. The verifier will give a random Z and say, give me this. Now ask the prover to write on F prime, which is a hash of F with respect to this random seed Z. And so this farness preserving is something that is true, but is non-trivial. And I will be talking about this. But once you have properties 1, 2, and 3, you can put them together to get an IOPP for testing proximity to Reed-Solomon codes. So let's focus on this farness preserving property. If F is far from low degree, what can you say about F prime? Okay, so we started with a function F on a domain S, and we found a domain of half the size, and we first found these two functions G and H, where if F was a Reed-Solomon code word, then G and H are also Reed-Solomon code words on this smaller domain of half the size and of degree also half the size. And it's not hard to see that if F is close to Reed-Solomon codes, then G and H are also close to Reed-Solomon codes. And if G and H are close to Reed-Solomon codes, then so is F. You might lose a factor of 2, but let's not worry about that for now. But then we took these two functions G and H, and we took a random linear combination of G and H with this random seed Z. And now it's not hard to see that if G and H are purely Reed-Solomon code words, then G plus ZH is also a Reed-Solomon code word. It's just a random linear combination of two Reed-Solomon code words. That's a Reed-Solomon code word. But what we want to ask is, if you just want this closeness, we want a more robust statement, that if G and H were close to Reed-Solomon codes, maybe it's not hard to see that in some sense G plus ZH is also close to a Reed-Solomon code. But what about the converse? Does it hold in the reverse direction? And this is going to be the question that I'm going to focus on for the rest of the talk. Okay, so I'll go into more details about what kinds of parameters we're asking, what kinds of closeness we mean, and things like that. Questions? So to go from F to G and H, we had needed some algebraic structure because of this. We wanted the square roots to exist, and so we would look at the field size, you're looking at a subfield which is a power of 2 and things like that. For this question, we don't really need this algebraic structure. Now let S prime be an arbitrary domain, and you can ask if G and H are close to Reed-Solomon code words. Is that true? Is that if and only if G plus ZH is close to a Reed-Solomon code word? And now let's forget, at this point, we can forget about IOPPs, we can forget about square roots. It's just a question about, S prime is an arbitrary, FQ is an arbitrary field, S prime is some subset of FQ. And you can ask some kind of proximity questions, we don't need the algebraic structure anymore. So this is the question of proximity gaps for Reed-Solomon codes and has been developed over a sequence of works. Let me give you a picture version of the main proximity gaps theorem. Okay, so again, we have the space fq to the n, and the Reed-Solomon code is some subset of fq to the n, where any two code words are far apart. I can draw balls of Hamming distance delta about every Reed-Solomon code word. Let's not worry about what delta is, but let me draw, for some parameter delta, I've drawn balls of Hamming radius delta. And now I can look at lines in this space. Okay, so FQ lines. So here's a line I drew that intersected two of the balls of Hamming radius delta. Here's another line where every point on the line intersected a ball of Hamming radius delta. Okay. The theorem we're going to see is of the following kind. Any line in this space, look at the Q points on the line. Either just a handful of points on the line intersect balls of Hamming radius delta. But if more than a handful of points intersect balls of Hamming radius delta, then all points must intersect balls of Hamming radius delta. You can't have a situation, you can't have a line where only half the points intersect balls of radius delta. Either very few points have this property of intersecting balls of radius delta, or all the points intersect balls of radius delta. And this is a property that Reed-Solomon codes have. And this is what I mean by proximity gaps for Reed-Solomon codes. Okay, so let's make this a quantitative and more formal theorem statement. Good. Good. So I'm looking at the Reed-Solomon codes over a field FQ, over some domain S, degree D and the degree D polynomials. Look at two points G and H, which are functions from S to FQ. So there are 2 points in this space FQ to the n. And I look at the line through G and H. Oops. I'm looking at the line through G in the direction H. So I'm looking at G plus Z times H as Z varies over everything in FQ. Then this theorem is saying that suppose for many of the Z's, so many points on the line, you intersect the ball of radius delta. Then for all the points on the line, you must intersect balls of radius delta. Okay, so that's what I mean. But what is epsilon and what is delta? I need to tell you. For what epsilon and delta do we manage to prove this result? Questions about so far? Okay, so the epsilon that we are able to, that we will show right now, that we are able to prove our results, this epsilon fraction turns out to be something like n squared over q. So n is the domain size, n is the size of S, q is the field size. So if q is much larger than n squared, then epsilon is tiny. Okay, so let's think of q to be 100 n squared or q is n cube. Then it's showing that even for a teeny fraction of points on the line, if you're intersecting balls of radius delta, then all points on the line must intersect balls of radius delta. But what is delta? Are we proving this for all delta? So what we show is, we show this result for all delta going up to the Johnson radius or the Guruswami southern radius. So for any delta less than 1 minus square root d over n, or 1 minus square root rho, where rho is the rate of the code, for any such delta, this result holds. Okay. It does. So I wrote n squared over q. There are constants in front of n squared over q. And the gap between delta and 1 minus square root rho will show up as a constant. So if delta is 1 minus square root rho minus epsilon, then that epsilon will show up as a small constant in front of n square. So there are the constants here. One is the gap from the Johnson bound, and the other constant will be just the rate of the code. D over n will also show up as a constant in front. So if the rate is constant and the distance from the Johnson bound is constant, then it will be some constant times n squared over q. Okay. So let me, in the remaining time, give you a few ideas about the proof. And I'll also talk about, towards the end, what can we hope to improve epsilon and delta, or in what ways can we hope to improve, strengthen these results? Yes, Prahladh? Yeah. 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 So right. Exactly. So when we'll show something stronger. We show that G and H must intersect these balls, and in fact, that means G agrees with the Reed-Solomon code word on a large set. H agrees with the Reed-Solomon code on a large set, and these sets are the same set. In a correlated way, they agree, and then the moreover follows. Yeah. So once you know the G and H agree with the Reed-Solomon code on the same set, then for any linear combination on that same set, they would have agreement. Okay, so let me give just a flavor of the proof. So we know that for many choices of little z, G plus ZH is close to a Reed-Solomon code word. Okay, so this is what is given to us. We want to deduce that G and H themselves are in some way close to the Reed-Solomon code word and in a correlated way close to the Reed-Solomon code word. The key ingredient in our proof is to use, so this is a completely combinatorial statement. There's nothing algorithmic about this proximity gap statement. But in order to prove this combinatorial statement, a key ingredient is to use decoding algorithms for Reed-Solomon codes. In particular, we'll look at the Berkeley-Welch algorithm and the Guruswami-Sudan algorithm and use the reasoning in those algorithms to deduce our results. So this is something everybody knows. Decoding of Reed-Solomon codes is just noisy interpolation of polynomials, and Berkeley-Welch and Guruswami-Sudan algorithms, both, a lot of you might have seen it last week itself, also the details of these. These are going to be key players in the analysis. Let me focus on the Berkeley-Welch algorithm to illustrate the proofs. At a high level, it's the same reasoning which goes into analyzing the Guruswami-Sudan algorithm, but there are more details here. So for now, let's focus on the Berkeley-Welch algorithm. So again, what are we trying to do? We know that for many little z's, G plus ZH is close to a Reed-Solomon code. So suppose this first purple line is the graph of G. The next purple line is the graph of H. Then what is G plus ZH? For different choices of Z, these green curves are the graphs of G plus ZH. So we know for many of these green curves, they are close to Reed-Solomon codes. We're going to deduce that this whole surface is somehow is a low degree surface. And by using the fact that many of the curves are low degree curves, we'll deduce that the whole surface is low degree, and then the results will follow. Okay, so many cross sections here, we have close to low degree polynomials. Can we have a low degree surface explanation? That's what we're going to do. And so the way we do it is the following. So again, I know that f of x plus z times g of x is close to low degree. So I know that if I run the Berkeley-Welch algorithm on this, it will succeed in finding a nearby polynomial. Okay, that's what is given to me. I want to deduce that for all z, it will succeed in finding a low degree polynomial. So what we do is let's now replace little z with a formal variable capital Z and view f of x plus z times g of x as a received word over a larger field, fq adjoint z, in this rational function field. Let's just view this as a received word and run the decoding algorithm. For now, let's run the Berkeley-Welch algorithm on this received word over this gigantic field. We don't know that this is close to being low degree in this gigantic field, but we will prove that the Berlekamp-Welch algorithm is successful and finds a nearby low-degree polynomial. And a proof that the Berlekamp-Welch algorithm is successful will use the fact that the Berlekamp-Welch algorithm is successful for many instantiations of capital Z to little z. So let's just start running the Berlekamp-Welch algorithm over this large field and see what happens. 5 minutes? Yeah. Good. So how does the Berlekamp-Welch algorithm work? You have a received word. You first find low-degree polynomials A and B. You solve a system of linear equations to find low-degree polynomials A and B, such that for all little x in capital X, A of x is R of x times B of x. So those, I don't know, maybe last week you saw with the error locator polynomial, you can show that these such A and B exist. And using a linear system, you can solve and you can find A and B. And then once you find A and B, the next step of the Berlekamp-Welch algorithm is to show that B divides A. And what you get is a polynomial, and that polynomial actually is the unique nearby polynomial to your code word. Let's try to run the same Berlekamp-Welch algorithm on this big function field, on this received word over this gigantic field where capital Z is now a formal variable. And we want to conclude that the algorithm works. So let's solve this linear system of equations and find low-degree polynomials A and B over this huge field where A of x is R of x times B of x for all x. So to run it, we can do it. Why should low-degree A and B exist? So we have to solve a linear system to find these A and B. The fact that this linear system is solvable for many choices of little z makes it solvable also for the formal variable capital Z. So the fact that this linear system can be solved in low-degree A and B can be obtained. For that, we use the fact that for many choices of little z, it can be solved. And then once you find capital A and capital B, now A and B, these polynomials A and B also have this variable. So it's over this big function field, it also has this variable z sitting inside it. So you have rational functions in z sitting inside A and B. But we will show that over this big function field, A over B is actually a polynomial in X. And to prove that it's a polynomial in X, you use the Polish-Chuk-Spielman lemma. You know that for many instantiations of capital Z to little z, B divides A. And using the Polish-Spielman lemma, it implies that B divides A even over the formal variable Z. And now, I'm almost out of time. Once you have that this polynomial P of xz is a polynomial in X, let me skip this, but it's a simple argument to show that this polynomial is actually close to the received word. And again, you need to use the fact that for many choices of little z, it is close to the received word where capital Z is plugged into little z. And it's a simple argument to conclude that this polynomial P will have the right form, the degree in z is linear, and it will be close to the received word. And we do something similar for the Guruswami-Sudan algorithm as well, to go for decoding radius all the way to 1 minus square root rho. Because I have 1 minute left maybe, so let me just comment on something about the proximity gap statement, what we know and where we can hope to strengthen it. So first note that this statement doesn't give anything meaningful unless Q is at least n square. To even get a meaningful statement here, we needed Q to be large. So can we make Q linear in n and still get such a statement? This would have very interesting consequences in other scenarios. So it's interesting to ask, can this epsilon parameter be improved? It's also interesting to ask, can we get such a statement for delta larger than 1 minus square root rho? Can we go all the way up to 1 minus rho? So there's one can study both these questions, and improving delta would directly improve the soundness of the Frye IOPP. So it is even practically a very interesting question. And there are several other improved IOPPs which have in the last couple of years where the soundness analysis of these IOPPs crucially use proximity gaps. So these parameters delta and epsilon are, I think, very interesting and very interesting to understand what are the best such parameters that we can obtain. In previous work, we managed to construct examples where we show that if the field size is n, exactly n, then you can't go up to 1 minus square root rho. You can only go up to 1 minus cube root rho for delta. So you can't hope to make the field size as small as n. And the proof uses subspace polynomials and is inspired by prior work by Eli, Swastik, and Jayakumar on constructions of bad list decoding configurations for Reed-Solomon codes. So these proximity gap statements and understanding list decoding for Reed-Solomon codes are very intimately connected questions. In upcoming work, which we are still writing up, we ask, okay, what if you want to go to delta beyond the Johnson bound? Can you go all the way up to 1 minus rho? And we show that we cannot do this. So we don't know, for Reed-Solomon code list decoding, we don't know. Maybe you can list decode all the way up to 1 minus the rate of the code. But we show that for proximity gaps, we can't hope to do this over any fixed polynomial sized fields. You can't hope to get a proximity gap statement all the way up to 1 minus rho. And in particular, if the field size is n square, then you can't hope to go beyond the Johnson bound. So there are some limits. In some sense, the statement is tight. For quadratic sized fields, the proximity gaps must stop at 1 minus square root rho. But we don't know. Maybe for cubic field size, you can go beyond 1 minus square root rho. But we don't know how to do that yet. And I just want to talk about this list. It's my last slide. This is the list decodability of Reed-Solomon codes. Is a really interesting question, which is intimately connected. We already saw how list decoding algorithms for Reed-Solomon codes, like Berkeley-Welt and the Guruswami Southern algorithm, those directly give us, their proofs give us, or their analysis gives us the proximity gap statements. And yeah, there are connections in the other direction too. So the list decoding of Reed-Solomon codes and proximity gaps are closely connected, and we don't understand this connection completely. So it's worth understanding more. So I just want to end with the open questions. What is the limits of these proximity gaps? Can we get better proximity gap statements? And how do they really tie to the list decoding radius for Reed-Solomon codes? Suppose you could list decode Reed-Solomon codes all the way up to 1 minus rho. Does that give you better proximity gaps? We don't know that. I'm out of time, so I'll stop here. Thank you. Yes.
We take that as evidence towards whether maybe you can't hope to do this decoding for such field size if you are going beyond the Johnson rate.
So not directly. So I don't know. I don't know if it's evidence, but if we could not list decode, then I think it gives the direction is stronger in the other direction. So maybe it is in weak evidence. Like if we could get great proximity gap statements, I think it would have implications for list decoding. But in this negative result, doesn't directly give it, but they're closely connected. Yeah. Yes. 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 We show the explicit good. So this is showing that you can't hope to get a general statement. I'll give you a specific field and a specific S, and I'll create specific polynomials G and H, which violate the proximity gap statement. These will be over binary fields. Over large characteristic fields, I don't know this statement. Yes, 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 exactly. These are just specific examples which say that in the generality in which I stated the proximity gap statement, you can't hope to improve it. But over there may be situations where S is cleverly chosen and the field is cleverly chosen where this may not hold. Yes. 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 Absolutely. Absolutely. So for instance, I mean, it would be nice to say that, okay, whenever you can list go to a larger radius, it gives you proximity gaps to a larger radius, and that's completely conceivable because our proofs don't use the list decodability as a black box. We go into a particular algebraic algorithm and analyze it. If you could somehow bypass the algorithm and just have a general statement saying that whenever you can list decode to blah radius, it's conceivable you can get proximity gaps for that radius, and we don't know how to show that. But yes, if S is carefully chosen like a random set, maybe this is true. And that was a very nice, interesting question, I think.
I had the exact same question. That's fine.
Okay, great. Yes, Venkat. Yes, we don't know examples like that. And that's a great, great question.
Okay, then let's thank Shubhangi again.
Thanks.